Alright, so welcome to our fourth lesson, and in today's lesson I'm just gonna cover basically mechanism drawing and tips for drawing your own mind maps and doing summaries for this topic. So a lot of organic chem hinges on being able to understand what's going on in the reaction. And I feel like for HT you guys don't learn enough of the mechanism drawing to the point where you feel comfortable with it. So I'll just be going through that on a deeper level. I just try and explain why certain reactions happen and try and help you guys see what goes on for reactions. So let's just do this first. So let's say so the mechanism for this is actually very simple. It's nucleophilic sub, like someone pointed out just now. So let's say we are starting out with this thing, right? It's just an alkyne. What happens is that if you have a strong base like B minus, you can just grab this H and collapse onto this carbon to form a nucleophile. Wow. So you have this, right? That's a lone pair. So what happens next is that you have this thing over here. This halogen alkane is very good for Sn2 substitution because it's primary, there's not much steric hindrance, and this is a relatively strong nucleophile. So it just attacks here, and then this goes here, and there you go, that's how you get your final product. Yay. Plus B minus. So if you can do this, you probably have a much easier time in chem, and if you can't, don't worry, that's what this lesson's for. Anyway, let's get started then. So let's go through the basics of mechanism drawing. What do you need to know to be able to draw a mechanism properly? Let's go to the top. Alright. So the first thing to be able to differentiate between is your two types of arrows. So you have your full-headed arrow, your full-headed curly arrow, as well as your half curly arrow. So this represents the flow of an electron pair of two electrons, and this represents the flow of one electron. So as far as H2 is concerned, you only need this for FRS, which I'll be going through later as well. And this is basically for everything else. So let's talk about a few other things you can take note of to make your life in organic chem easier. So if you have something let's say you have your OH2 plus thing over here, whenever you draw an arrow from the H collapsing onto O, make sure you always go to the oxygen atom. Because in this case, we're showing that the two electrons that originate this bond are both returning back to oxygen. Because if you remember, right, how this would originate, for example, is you would start off with something like this, and then your oxygen here will grab a H+. So what's happening is that a dative bond is being formed. So in reverse, right, you obviously have to do the reverse of this to get back this. So that's just a way you can remember how this works. But that's an example of both electrons returning to an atom. Now if you have something like elimination per se, what's a good example of this? Let's say you have something like your oxygen being eliminated, right? Okay, let me just draw a basic mechanism. This isn't super legit. Actually, okay, whatever, should be good enough. So let's say something like this, right? So you have a strong base, let's just say some random thing that grabs this. If you notice, right, since I'm converting this bond into a double bond over here for elimination, what you have to do is you basically draw your arrow to the single bond here to signify that bond is being formed, then just kick this out. Alright? So that will just give you the product of your elimination reaction, which is your alkene. So these are just the basics, right? And if you can't understand this, what you can do is think about what's happening to electrons. So originally we have two electrons here, correct? One of these electrons we know belongs to the carbon, the other one belongs to the hydrogen. But in this case, since the base is grabbing onto the hydrogen is basically letting go of its electron. Now, if the second electron was returning back to the carbon, then we would draw the arrow towards the carbon. But in this case, since the second electron, or both of these electrons, are moving to form a new bond, we basically draw the electron pair being shifted over here to show that a new bond is being formed. Alright, does that make sense to you guys? Okay, let's assume it does, then let's just move on. So another tip you guys can take note of is that in acidic mediums, right? Acidic medium, you can only have neutral or positive charges. So what this means is that if you have an OH minus in acidic medium in one of the mechanism stuff, something is wrong. You shouldn't have that. Then for the basic medium, the same thing applies, but for basic stuff. So you can only have neutral or negative charges. This is just a rule of thumb to make sure you're not doing anything wrong in your mechanism drawing. Then it also helps to note certain reaction speeds for mechanism drawing. So you should know that intramolecular is faster than intermolecular. So intramolecular occurs at a much faster rate than intermolecular. So basically, if there's a reaction that can happen within the molecule, it'll happen faster than between two molecules. Then you should also know that acid-base reactions are generally the fastest, or one of the fastest reactions. Acid-base reactions are really quick. So now that we know all of the basics for mechanism drawing, do you guys have any questions about anything regarding this? You can just type it out in the H2 chemistry stuff chat. If not, I'll move on to Sn2. I'll just give you guys a few seconds to type out any questions you have. Any questions? Going once, going twice, gone. Okay. Let's move on to Sn2. So let's look at what happens for Sn2 reactions on a deeper level, right? So this is like basically the simplest reaction that you see in organic chem for you guys. So let's just look at this. So we know that for Sn2 we have a nucleophile, it can be anything. It can have a minor charge and stuff, attacking this carbon to get rid of this bromine. So what's actually happening to the electron movement? So first of all, right, let's consider why the nucleophile attacks this carbon in the first place and not something else. Like if you have a very long carbon chain, why attack this position and not like here? Well, the first thing you have to think about is your delta positive charges. So you know that because this carbon is connected to an electronegative atom, it means that this carbon is a slightly positive charge. Because the electron pairs are going to be held closer to the bromine atom. And because the electron pairs are being held close to the bromine atom, you have a slightly negative charge over here. So what this means is that the nucleophile is likely to attract this carbon because, oh look, I want to donate a pair of electrons and there's an electron deficient area here. Let's just pick this compared to all these here. This will be like neutral in that sense. So once this happens, right, since your carbon can only have so many electrons around it, because remember there's like two hydrogens connected here as well. So what happens is that it wants something to leave. Now, CH bonds in this case, right, CH bonds are quite strong. They have like an energy of like 400 kilojoules per mole, which is much greater than like a lot of other bonds are quite strong. So it looks for CH bonds first. It can't break any CH bonds. Let's move on to CC bonds. Now CC bonds are also quite strong. So CC bonds are also quite strong, so they're unlikely to be broken. But then if you look here, right, you have a CX bond here. Now CX bonds are not that weak, but in this case, like compared to other options, and compared to the bond being formed, we know that this bond being broken is going to be weaker. So let's say our nucleophile in this case is an OH minus, right? We know that an alcohol like being formed here will probably be more stable for this molecule than like a bromine being connected. So what happens is that both of the electrons here will get collapsed onto this to basically give you your product plus Br minus. Now let's look at the electron pair movement more closely here. So as you can see, right, both of the electrons from the oxygen are being donated to the carbon over here. So it's almost like a dative bond in that sense. And because both of the electrons are being donated here, right, that means that the carbon must lose 2 electrons for somewhere else. Because we already know that in this molecule here, the carbon has 8 electrons. So it's accepting 2, it must get rid of 2 electrons as well. Which is why both electrons of this bond go on to the Br. Now Br originally, right, if you draw the electrons around Br, there's going to be 6 electrons here. Yeah? Any questions?
I was around elementary 30 years ago, kita because I am
Okay, moving on. Anyway, so we know that bromine origin has like 6 electrons around it like this as lone pairs, and also has 2 electrons here. Now bromine in its valence state is like a radical with 7 electrons. So what's going on is that one of these electrons originally belonged to bromine. But now because we're adding an extra electron over from what it normally has, which is like this thing, they have a negative charge, which is why we have a negative charge here. Now this is like a very fundamental concept for organic chem, so you guys need to like be able to visualize the electrons moving around. So if you can understand this, right, can you guys type a 1 in the chat, in like the H2 chemistry stuff chat? Let's type a 1, and if you want me to explain this again, type a 2. And if you have any questions, you can just type it out. Okay. Anyone else? Like, do you guys understand this? Then just type a 1 and we'll move on. I'll give you guys 10 seconds. Remember, feel free to ask any questions.
As a general rule of thumb for this kind of arrow pushing, right? The electrons, or whichever atom is like getting the electrons in the arrow, right? You'll get like a -1 charge. Or like the charge will -1. And then the one which is like losing the bond, right, will +1 charge. Kind of lah. Yeah.
Yeah, that's very true. That is something to take note. And remember, right, for as far as H2 is concerned, even if you're asked to draw like a half arrow, right, remember that you just need to have like half arrows in pairs of 2. You can't just have one half arrow and nothing else on the side. So you have to move 2 electrons at a time. That's very important to keep in mind. If you're only moving 1 electron at a time, right, something is wrong. As far as H2 is concerned, just keep that in mind. So let's move on. Okay, let me give you guys a question. Why are you drawing the question? Oh no, drawing the Sn1 mechanism. Okay, actually let's go through that first anyway. So in the case of Sn1, right, we know that the leaving group leaves first, okay? So I want to make this drawing here. We know the leaving group leaves first. So what happens is that you form a carbocation. Now because this is tertiary, it's like a tertiary halogen alkane. We know that the carbocation form will be relatively stable because tertiary carbocations are quite stable. So what happens after this is that, let's say if a nucleophile like H2O, okay, so what the H2 will do is just attack this site here. Now because the carbon has a positive charge, right, if you add an electron pair to it, like if you attack with an electron pair, it's just going to go up by 1 state. So you go from positive to neutral. Alright? So that will give you the product of your tertiary alcohol. So you get OH after deprotonation, of course. I'll just put -H per cell. Don't use this notation in H2. I'm just making things simpler. Now, let's go through that as well, because I forgot to mention just now. We know that at any given moment, right, you can have 3 states. You can have a positive charge, you can be neutral, or you can be negatively charged. You also have radicals, but those are separate from this line of thinking, so we'll go through it first. At any given time, right, let's say you start out from a position of being in positive charge. With 1 electron pair, 1 E- pair, you can only jump from positive to neutral. You cannot go from positive to negative in 1 step. You need at least 2 steps for that to happen. Same thing for neutral. If you have 1 electron pair for neutral, right, at one given moment, you can only move towards a positive or negative charge. You can't like either do some weird stuff with it. So 1 electron pair can bring you from neutral to a positive or negative charge. That's the same thing for negative charge. You go from a negative charge to a neutral charge, you need 1 electron pair. You cannot jump from a negative to a positive charge, because that signifies, in that case, a movement of 4 electrons. Like something you guys need to think of, like, it can be quite confusing at first, is that normally when we talk about the formation of charges, let's say you convert like Na to Na plus, right? You think of it as sodium losing 1 electron, correct? But in this case, for organic chemistry, because of how the electrons are moving about, going from positive to like neutral is a movement of 2 electrons in that sense. And it's really important for you guys to just like watch the movement of electrons from one point to another to see why this is the case. It's not actually the fact that, oh, a positive charge is now requires 2 electrons to be lost. It's more of how electrons are being moved that matters. So if we go back to the example of like Br, right? It might seem at first glance that the Br here is actually gaining 2 electrons. But the truth is that one of these, because this is a bond, right? One of these electrons only belong to the Br in that sense. So it's only gaining 1 extra electron, even though 2 electrons are being moved into the Br. Which is why it gains a minus charge and not a -2 charge, or like a 2 minus charge. So you have to keep that in mind. Like, you can't really get, like, in organic mechanisms, right, you can basically never get like a doubly positive or doubly negative charge. Do you guys get that? Can you just like type a 1 in the H2 chemistry stuff chat if you get it? And just type 2 if you want me to explain again. Okay, great. So I'll give you guys a question. You guys can try it now. Actually, like, do you have any nice questions for them to try out for nucleophilic sub?
Nucleophilic sub.
Yeah.
Can I just give you all like a generic reaction? And a new reaction mechanism. I'll give you all the intermediates and then you all can try see whether you all know how to do it.
Actually, this as it's just based on what they've learned so far. I think it's fine.
What we've learned so far. Okay, let me think.
Like on. I'll do carbonyls after this, but I want them to like try the nucleophilic sub first.
Okay, wait. This one shouldn't be too difficult. Okay.
Just start drawing and move the thing there.
It's very simple.
Oh, this is a fantastic question. Good job, Nick.
Suggest this. Draw
Okay,
mechanism for this, yeah.
Yeah, draw a mechanism for this. I'll go through this question in 2 minutes. So at 10:23, I'll go through this. You guys can take 3 minutes to do this now. Alright? Remember, this is based on nucleophilic substitution. It's not very difficult. I just think about like what I talked about just now, and then try and apply it now and go through this. If you want me to check your answer, right, you can just send it to me in the. You can just PM it to me or just send it to the H2Can chat. I'll tell you whether or not you're correct. If you finish before that. So yeah, you can just take a picture and send it. You guys can start now. I'll go through this at 10:23. Will you give another question as well? Or bonus question?
It's bonus. If you don't know how to do it, it's okay.
Oh. that's next week's history chem lecture actually.
H3 chem.
Yeah.
Oh.
You didn't even teach us in history, you know. But oh well. Alright, are you guys done? Or do you guys want more time? We can just type a 2 if you need more time in the chat, and 1 if you're done. Okay, let's go through it then. Remember, if you guys think I'm going too fast and stuff, you can just speak up and let me know anytime. I mean, our class is quite small, so I can go rather in depth today. So that's like I said just now, right? The best way to do any sort of organic chem mechanism question is to first of all compare what you're starting off with and what you're ending with. So in this case, right, if we compare the number of atoms here and here, the only difference is that there's one that's H and there's missing Br now. Now that should give you a clue. The place where the H is lost from is a nitrogen, right? So now the nitrogen loses a H and the Br is lost from this carbon, and now there's a new nitrogen carbon bond formed here. So what this means is that the nitrogen likely attacked this carbon here to kick out the bromine. And that's how you get this. So after it kicks out the bromine, right, you get like an intermediate here. So if you just draw that, you basically get oh, the stupid circle in the benzene. It's so annoying. Oh, I should do that. I should do the Arie's question with them later. I just remembered. The nucleophilic attacks. Okay, anyway. So you get this, right? So normally, like, if you have something like water, that can also grab the protons, but let's just assume that you don't. Let's just assume the only thing you have is a Br minus. What the Br minus is just grab this, and then collapse it onto, this. Now you see, what I just did here is a mistake that you should not make. Always draw the electron pair moving towards the atom itself and not the charge. So instead of doing that, what you should do is draw it towards the nitrogen here. Because you draw it towards the charge, Cambridge will just be like, no you, and just give you a -1 for that. So there you go. That's the mechanism. Do you guys get this? Can this reaction take place via the... Actually, By right, yes. Because you see, right? Okay, I drew this as SN2, but by right it can take this as SN. It's probably better for SN1 actually because of the benzene here. So that you got a very good point, right? Your cation there will be quite stable because it's a benzylic cation, but I don't think that's within H2. Actually, is it?
It is, I think. Okay, actually, right, if
Oh,
you drew it by SN1,
it's probably better actually.
you spotted it well. Yeah, I didn't
Yeah,
realize that as well.
yeah. If you
But
do SN1, it's actually better.
in my opinion, right, both SN2 and SN1 are okay for this. Whatever
Yeah,
mechanism you drew, right, SN2 is okay, SN1 is also okay.
but I think SN1 is better for a H2 syllabus because you
Yeah.
see, right? What you guys don't know in school is that there's a lot of factors that determine SN1 and SN2. For you guys, you just learn it based on like the degree of the carbon or your alkyl chain. But in this case, very good job, JVD. Like the fact they mentioned as SN1 is like amazing. So it's a very good spot. So yeah, if you were to draw an exam, I would recommend going through the SN1 route. That's probably a bit better. So yeah, good job. Let's move on to carbonyl compounds. Yay. Actually, I thought to erase your amazing question. Actually, yeah. I'll just not erase it first. I'll just you can do it later. Oh la la. Okay. What the heck? Okay, there you go. Oh my gosh, are you serious? I can't just delete. Why is the object snapping? That's so stupid. Okay, let's move on. So let's talk about nucleophilic addition, because that's slightly easier than nucleophilic sub. Okay, so let's say we have this compound over here. It can just be some generic ketone. Let's just say there's two R groups, R and R prime. Now, first of all, right, if I were to want to do like nucleophilic addition to this, what do you think I would want to attack here, and why? Like which part of this molecule would I want to attack and why? You guys can just type it out in the chat. It's a relatively simple question. I can just like unmute yourself and say it out too. So in this case, which carbon atom would I want to attack and why? For nucleophilic addition. That's a very generic example. I would obviously want to attack like the delta positive carbon, right? Or something that is slightly electron diffraction. So I can't attack the oxygen because it has like a bunch of lone pairs around it, like it has 2 lone pairs to be exact. I just draw 1, 2, 1, 2 around it. But and you know this is the electron negative atom, so it's likely to be delta minus. But you know this carbon over here, since it's attached to a delta minus atom, is likely to be delta plus. And because it's delta plus, it means it's electron deficient. And we know that nucleophiles love to attack electron deficient places. So let's say we draw a nucleophile like Cn minus over here. So it's like a simple cyanohydrin thing. If a Cn minus were to choose to attack one location, it'll be this part, right? So watch as I draw the electron pair to the carbon over here, not the charge. Remember guys, whenever you draw an electron pair towards like being absorbed by like an atom, right? Always go towards the atom and not the charge. Because you'll be penalized if you do it by the charge route. So now that I have my first step here, this isn't the entire mechanism for the first step. There's something else that I need to do. Remember how I mentioned that your carbon can only have like 8 electrons around there at once? Right now it already has 8 over here. So in order for it to have 8 now, it needs to lose 2. So the only way you can get rid of 2 is if it collapses both of the electrons back into the oxygen. So once again, draw your bond towards the oxygen atom. And what this will give me, right, is first of all, let's just draw the carbon first. The carbon will not change from neutral to anything because its overall number of electrons around it has stayed the same. So it just gets the Cn. The oxygen, right, first of all, oxygen only has one bond to it now. Let's think about this. The oxygen originally had like 8 electrons around it, right? But 4 of them were located in bonds, so it sort of like had like 2 being shared with like 2 of it was being shared with the carbon, but now it has an extra electron to itself, which means that it now has a negative charge. So take note of that. Because you only have 1 electron going towards the oxygen and no electrons going away from it, you now gain a charge of -1. You guys get that? If you don't, you can just type out the question. Just spend a few seconds thinking about this. What was happening to the electron pair here? Remember, 1 electron was originally like being shared. 2 electrons were being shared between the oxygen and the carbon, and now both of them are going to the oxygen. So the oxygen is sort of getting an extra electron, which causes it to have a minus charge. Any questions? We just type. Okay, actually, that's fine. Any questions? If not, I'll give you guys 3 seconds. 3, 2, 1. Okay, let's move. Oh, wait. Okay, ADB, that's a very good question, right? So ADB has asked, like, since I've labeled a carbon as having partial positive, and there are two electrodonating R groups there, won't it make it more negative? And absolutely correct. In that sense, right? Let's say I compare this molecule to something like, I don't know, let's have something like acyl chloride, which is what we also know as syllabus. The delta positive of this carbon over here will be much higher than that of this carbon. But you see, right? Okay, let me ask you this. Electron donating R groups donate via which effect? Like they make use of a certain effect to donate electrons, right? So what is the effect called? It's called the inductive effect, correct? Now the inductive effect, right, compared to electronegativity, the inductive effect is quite weak. So yes, it will make the positive charges smaller than if there was just the carbon oxygen, but it's still not small enough for the positive charge to not be noticeable. So it still makes that carbon quite susceptible to nucleophilic attack. Because the electron donating group effects, or through like the inductive effect, right, isn't as strong as the partial positive charge that you get from an electronegativity difference between the oxygen and the carbon. Does that answer your question? Alright, fantastic, let's move on. So now that we have this molecule, right, we know that this is basically an intermediate, and we don't want it to stay as a negatively charged molecule because of reasons. It's just not as stable as something that's neutral. So we also know that normally for this mechanism, we normally have like KCN and HCN being added. This is where your HCN comes in. So what happens is that oxygen will basically just use one of its lone pairs to attack the hydrogen and move this here. And then because of that, we get R, R, CN, and OH. Now in this case, right, we did nucleophilic addition. So there's now a new bond being formed. Remember, for addition reactions, you will always end up with like one extra bond being formed, or like something changing. Like basically, you see like one new bond being formed in with like a bond being replaced. Like normally for addition reactions, at least within H2, right, your double bond will be replaced with two single bonds in that sense. So moving on, right? Okay, let me ask you guys to try this question first. So Nick drew this bonus question just now. And now that you know how the nucleophilic attack happens, can you guys try drawing this? Take the next 4 minutes to do this, and if you can, right, just take a picture of this using your phone or something and then send it to me on Discord. How does that sound to you guys? Remember, right, for nucleophilic like carbonyl groups and stuff, remember to label your delta positive and delta negative charges. But yeah, it's okay if you can't figure it out because it's like slightly above like what I just thought. I've used your brain a bit more here, so just think about how this would work. Compare leaving groups for a second step. Okay, so the first step, right, should be quite standard. I just went through the first step. Now the second step is where it's a bit tricky. So think about what's happening in this case. Alright, just think about leaving groups. That's a huge tip. Off. Look at what's changing in terms of like the number of bonds and stuff. Remember how I mentioned just now that in addition reaction is a double bond being broken into like one single bond and another single bond, right? In this case, you have two single bonds being converted back to one double bond. So what that means is that since your number of like double bonds and single bonds is the same in your initial and final product, it's a substitution reaction. That's another clue. So your first step is addition, then your second step is substitution. It's like sort of like kicking on the leaving group, and overall it's a substitution reaction. So let me take until like 10:36 to do this. If you can, send me the picture, and if you don't want it, it's fine too. But just give this a shot until 10:36. Alright, I'll go through this afterwards. Alright, do you guys manage to give this a shot? Or you guys need more time, you can just type it in the chat. Okay. Also, if you want, right, can someone like unmute and try like answering this question? You can just tell me like what I should be doing, like what if I was a student that didn't know how to do this question, right, what would I have to do? You can just like try guiding me through this question. Just for practice. If you want to, of course, like no pressure. Anyone? You get bonus brownie points if you do this question. What you can do with those brownie points no one knows, but you can get brownie points. Okay, I'm gonna assume you guys give this question a shot at least. Let's go through this. Oh, Nicholas is so nice to them. He gave them hints. Okay, let's start off. First step. You know the first step is a nucleophilic addition based on what we just covered. So first of all, label your delta minus and delta plus charges. And in the next thing, remember that for your nucleophile, gosh, serious, okay. For your nucleophile, remember to always draw the bond coming from the lone pair. Don't just draw the bond coming from an atom because it's the lone pair that's being attacking the thing, not the atom itself. So lone pair attacks this. The next step is this collapses. So you draw this out, you basically your intermediate. So you have this. Okay, I want someone to try this. So like, does anyone want to give this a shot? It's okay if you get it wrong. Just give it a shot. Like, what do you think? What do you guys think happens next? I mean, it should be quite obvious by now, but yeah, you guys can give it a shot. What do you think happens next? You just type it out in the chat. Where do you think the electron pair should come from? Oh my god, that's great. Yep, that's the first step. Okay, does anyone want to try the second step? Remember what I said about carbon only being able to have like 8 electrons around it at one time? So that means that's the second step here. But good job, AD, we got the first step like spot on. Alright.
Wait, ADV, are you referring to like the first or second step? Because honestly, this is kind of hard to like write out in words.
I think it's the second step, but actually that's true. Like, even if you wrote the first step, it's still gonna be correct. It's okay. The mechanistic logic is correct, regardless of which step he's talking about. Typing that too. Yeah, JBD is correct. Okay, but where would I start the second electron arrow from? Do I start it from the carbon or the bond between the carbon and the chlorine? Yep, ADV got it as well. Good job. Okay, JBD, you can just tell me like where the electron arrow will start from. Carbon or the bond? Let's type C or bond. That's enough. Correct. Good job. You guys, both of you get it. So that's fantastic. So let's just draw it out. So like they mentioned, right? Yeah, it's actually just poggers. It's really epic. So you draw the lone pair. to the carbon. Okay, it's not the carbon, but okay, technically it's to the bond here. Sorry, it's not to the carbon. Actually, in that case, it doesn't matter that much. As if you draw to the carbon, it should also be correct. But I think it might be more accurate to draw it to the bond because I mentioned just now. You're sort of transferring one electron to the carbon to form a second bond. So anyway, just draw it to the bond. Then your second step, your bond between your Cl and carbon breaks, and boom, you get this. Now here's a thinking point for you guys. Given that we have been talking about mechanisms for so long, let's switch things up a bit. If I wanted the reverse to happen, let's say I started off with OH and I put a Cl minus here. Could you form, with this form, could you form an acid? Oh my gosh. Could you form an acyl chloride like this? What do you guys think? You can just speak up in the chat, so you don't have to type it out. You can just like unmute yourself and talk. Do you guys think that the reverse can happen? Think about this for a second. Can the reverse happen? And if so, why or why not? You guys can think about it. Feel free to like just unmute the answer. Like trust me, no one's gonna judge. We're all trying to get better at chem, yeah. Because chem can actually get really hard. Okay, no, yep, along the right track, but why can't it happen? Like, if I wanted to, the first step can easily happen, right? The Cl minus can attack, like, the O. I mean, the C. The Cl minus can attack the delta positive carbon. That's not what's stopping the reaction. So you have to, like, think about, like, what's preventing the reaction from happening. Why does this not happen? It's not because of that. Like, that's not the reason why this reaction can't happen. Think about leaving groups. It's more to do with leaving groups more than anything else. It is less, yeah, like you're correct in saying that the carbon is less electron deficient, but even because of that, the reaction can still proceed. That's not the reason why it won't happen. Correct, spot on. Okay, it's not a good leaving group because it's a strong base, but it's a good leaving group. It's not a good leaving group. Okay, sorry. It's not a good leaving group, not because it's a strong base, but rather because it can't stabilize the negative charge on itself very well. You see, oxygen is quite small, right? Your electron charge is like resting on oxygen by itself isn't that stable compared to something like chlorine. Like chlorine and bromine are both massive, so they can disperse their negative charge over a larger volume or area, which makes it more stable as a leaving group. That's why like OH- is not a good leaving group. So whenever you answer quantitative questions, right, you say that you talk about how it's unable to stabilize the charge as well as something like Cl minus. Alright, you got that, JBD?
Okay, just to clarify that, right? You're saying that like it's not a good living group because it's like very basic, right? It's not wrong, right? Because basicity, right? Like whether or not it's basic, it's a good indication of whether it's stable or not. However, like the like actual underlying reason, right, is that OH minus is less stable than Cl minus, and so it's a less, it's not as good of a living group. But
yeah,
whether or not it's basic is a good gauge of that.
yeah, because like it sort of determines how stable like your electron pair is on that atom itself. Like if something's very basic, it just means that it wants to get rid of the electron pair quickly. It doesn't want a negative charge on it. So that would suggest that it can't dispose a negative charge very well, like Nicholas said. So like you actually got it correct. Because remember for H2 chem, right? It's very important to get your phrasing correct. So remember to like try and be as direct as possible in the reasoning in terms of the stability of the living group. So remember, I still want to like make sure you guys get this. So like your first step involving like this can still happen. It's not that this can't happen. Like if you were to draw this, right? If you were to draw this, like this will still happen. But you see, right? If you think about like the previous reaction, even if this happens, once the electron collapses back, it's just that the Cl is going to be kicked out over the OH. Since Cl is a better leaving group, it'll just kick out the Cl. Which means you'll go back to getting back your product. You just get back what you started off. I mean your reactant. You just start off with this again. So that's what I want you guys to take note of. Do you guys get that? This is like a very fundamental thing, so there's a bunch of factors actually, like, but yeah, generally yes. But you also have to consider like Okay, do you guys want me to go through like why nucleophilicity doesn't parallel basicity sometimes? I know like they say that not like just because the base is better doesn't always mean that it's a better nucleophile. Do you guys want me to go through that? Okay, let's compare that. Okay, so first of all, right, when you talk about nucleophilicity not paralleling basicity, right? I mean, you say that oh, the nucleophile isn't like always better just because it's a stronger base. They're normally comparing cross atoms. Like if I were to compare like OH minus, first of all, let's just clarify that. If I were to compare OH minus versus OCH3 minus, the fundamental atom that the lone pair is coming from is the same here. So, but in this case, this is a better base and a better nucleophile. So it's better. Do you guys know why OCH3 minus is a better base and nucleophile than OH minus? Let's just get out of the way first. Then I'll explain why in some cases it's not. Why nucleophilicity doesn't parallel basicity in some cases. You guys get this first though. Like if my yeah, exactly. So if makes your thing less stable, so your electron pair is more available for donation and stuff. But let's say like you have something like I don't know OH minus versus SH minus. Now in this case, right, OH minus is the better base, but SH minus is the better nucleophile. Let's think about that for a bit. The only difference between O and S that really matters to us is like the difference in size, which causes a difference in electronegativity. So in this case, right, the big clue here is that the only difference between OH minus and SH minus is like how electronegative it is and how stable the thing is. So like generally, right, this is something is more basic when it's less stable, just now as Nick said. So in this case, right, what do you think is more stable, OH minus or SH minus? Like we just had like ions floating around in like a random solution. Would OH minus be more stable or SH minus? Given that S is a larger atom, you guys can just type it out. You can just say OH minus or SH minus. I just want to see what you guys understand. So like, is OH minus more stable by itself or is SH minus more stable? You can just type out the answer. It's okay if you get it wrong. Just think about this for a few seconds and type it out. And can like some of the other people in the lesson try as well. Like I know you guys like I might be a bit shy, right? But it's really important that you guys try to like answer and speak up in the lessons because like that way I can actually like go through stuff that might be missing. Like you might guys may be like missing terms of your link of understanding. But anyway, wait, I asked for which one's more stable. So like you guys think that OH minus is more stable, just to confirm. Okay, if I let's just take a step back. If I compare OH minus versus Cl minus, which one do you guys think is more stable? Like OH minus versus Cl minus, which one would be more stable? Let's think about it. Yeah, and why is that? So why is Cl minus more stable than OH minus? The reasoning here is very important. Like just now we talked about leaving groups, right? What was the thing we were discussing? Okay, I'll just go through this quickly. So just now we're talking about how like Cl minus is a better leaving group than OH minus because it's more stable by itself, correct? That's because like Cl minus is able to disperse the charge better because it's a larger atom and all that. In this case, right, if you were to compare like oxygen to sulfur, mean that sulfur is like direct like below oxygen within the same group. That means the sulfur is bigger than oxygen, correct? So because sulfur is bigger, it's actually better able to stabilize the negative charge it has, which means that it's more stable than oxygen. You guys understand that? You guys understand why this is more stable? You guys understand why it's more stable? It's very important for you to understand why it's more stable. Yes, it is better able to disperse the negative charge. That's why there's like a phrase called it's for any charge actually. But if you look at Feigen's rule, right, from chemical bonding, you see that a cation has a higher charge density if has a higher charge and a smaller size. So in this case, the reverse is true. If an atom is bigger, it's be able to better disperse any charge. So it has a lower charge density, which makes it more stable in that sense. So do you guys get that? Do you guys understand why that like an atom being bigger means it's able to disperse a negative charge better? Yeah, to compare the stability of a base, we do look at the availability of the lone pair in that sense. But in this case, we're comparing like a base versus a nucleophile. Like if you remember, right? Okay, wait. Do you guys know what's the difference between a base and a nucleophile? Like, what's the definition of a base? Like, what does what does something do when it's acting as a base? What does a base donate an electron pair to? That's the first question. Yeah, it donates it to a proton or a H plus, correct? And what does a nucleophile donate an electron pair to? That's correct, but like in this case, it's most of the time the electrophile is a carbon atom, correct? I mean, normally, like whenever we do like nucleophilic reactions, we are normally like, attacking a carbon, right? So, fundamentally, right, the difference between a base and nucleophile boils down to like whether or not it's forming an atom between a H plus or a carbon. Now, if you think about electronegativity, would electronegativity be more important in a factor as a factor of being able to donate a lone pair in terms of like donating to a charged atom or to a partially charged atom? Where do you think like your electronegativity becomes a bigger factor for electron pair donation? For a charged atom or partially charged atom? Where do you think it matters more? Correct. And why is that so? Like what is the problem if you have a more electronegative atom attacking a partially charged carbon, for example? To the rest of you, sorry if this is a bit slow, but I feel like you guys should also pay attention to this like conversation because like this is a very fundamental concept that you have to try and understand. So ADB, why do you think it matters more if like for more electronegative atom if it's attacking a partially positive carbon compared to like a positively charged atom? Yeah, correct. So if your difference electronegativity is like low, right, that means it's going to be less willing to donate electron pair. So for nucleophilicity, what that tells you is that electronegativity is a huge factor in something's ability to donate the lone pair. And we know that because SH minus is less electronegative, like the S is less electronegative than the oxygen, right? The S is going to have an easier time to donate the lone pair to a partially positive atom, which is why the SH minus is a better nucleophile, because it doesn't hold on to the lone pair as much. On the other hand, right, for basicity, right, since you're attacking a positively charged atom, then your like ability to attack using the lone pair becomes a lot more important. Do you get that understanding? So whenever you're comparing like between two like atoms, for example, they're attacking a nucleophile, always consider electronegativity. Does it make sense? That's fantastic. Okay.
I just want to add on a bit to that. So right, you know how like in this kind of case, right, the lower the electronegativity of the atom, the more nucleophilic it is. Like so that's why in this case SH minus is more nucleophilic than OH minus, right? You can actually extend this to a lot of other things. So in fact, iodine, right, like something like I minus, is also a good nucleophile. The only thing is that the interesting correlation, right, is that something like OH minus, right, or like let's say ammonia as a nucleophile, when they are better nucleophiles, they also happen to be worse leaving groups. Like for example, OH minus, right? Like for example, let's say you take like water versus OH minus. Water, like H2O, is a weaker nucleophile than OH minus. But then it's also a better leaving group than OH minus. But then let's say you look at the case of something like OH minus and SH minus. SH minus, right, is a better nucleophile than OH minus, but it's also a better leaving group than OH minus because it's less basic. That's just food for thought.
Yeah.
Yeah.
Think about charge disposal again, about how it's able to better stabilize the charge. Because like in this case, right, the larger size contributes to two characteristics. The first characteristic it contributes to is like its ability to stabilize the charge, and the second one it contributes to is the electronegativity. So those two things like contribute to like the electronegativity contributes to its ability to act as a nucleophile, while its size affects its ability to stabilize the charge. So because of that, you sort of get this like contradictory thing actually happening. Do you guys understand that? It's actually a very cool and interesting thing to think about. You guys get it? Nice. Okay, so what was that again? Oh yeah, so we're going this, right? So that's pretty much it for carbonyl compounds. So these are like basically the two reactions you need to worry about in carbonyl compound. Oh yeah, actually, right, since yeah, I'm gonna sound funny. Since like ADB mentioned the positive charge thing, right? Let's go back to that for a bit. So let's say I have this thing over here versus like this thing over here. Which carbon will have the higher positive charge, like a higher partial positive charge between these two compounds? Oh, no, okay, let's not talk about partial, let's talk about reactivity. Which is more reactive in this case? Between these two. Like, if you think about like directions that acyl chlorides can go through, right? Which of these will be more reactive? Let's not confuse ourselves with partial reactive. Like, which one's more reactive? Correct, right? And now, and do you know the reason behind like why it's more reactive? It's because of the fact that your CO minus can be kicked out more easily. So because of that, that explains why for esterification, right? It's so much easier to do esterification with like an RC, like a acyl chloride than an acid, like than a carboxylic acid. Do you guys get that? It's more reactive because the CO minus can get kicked out more easily. That's why it can react with like water and stuff. In this case, right, like the issue with comparing electron deficiency in this case is like if you compare the electronegativity of like O and Cl, it's a bit hard to justify the partial positive charge being higher on the acyl chloride in that sense.
There's actually a bit more going on in this reaction than just like the electron deficiency of the carbon.
Yeah.
So like it's a bit more complex than just that lah. But as a good gauge, right, the one with the better leaving group is more reactive. That's why in this case acyl chlorides are more reactive than carboxylic acids because Cl minus is more stable than OH minus.
Yeah.
I can send a link later.
Oh my god, I have a really fun question I want to do with them. Actually, this one, like, I really hate how they don't teach it in H2. I want to do the...
Okay, if you want to know the legit reason why acyl chlorides are more reactive than carboxylic acids, right? The legit reason is due to delocalization, right? Because the lone pair on the OH, right, in a carboxylic acid actually can like overlap, right, with the pi bond of the CO group. And so because of that, right, there's like some stabilization of carboxylic acids, which makes it less reactive compared to an acyl chloride. But it's okay if you don't know.
If you want to do that, if you want to explain using electron deficiency, you have to go through the resonance route. Because of the resonance thing, right, your overall positive charge may not be as high as something like the acyl chloride. It also explains why your carboxylic acid can stabilize your charge relatively well. Yeah, there's actually a resonance structure for it. Especially for the carboxylate salt. Like, you know your RCO minus, right? That thing is quite stable because of the resonance. That's why it's like it's a relatively good, like, in that sense, like acid, because you're, you know. Oh yeah, then you can definitely go through the route if you want to. It's actually like there's multiple factors for organic carbon. Yeah. If you learn the phrase and stuff, you can always use that. That's fine. Like for this session, my main goal is just to go through like the mechanism. Okay, let's think about this question. This question is like something that isn't covered in like H2, right? So you guys know how you can't use like HCl-AQ to do this, right? And you have to use like PCl5 or like PCl3. Have you guys thought about why? Because fundamentally both of these contribute to Cl minus. Do you guys know why like HCl doesn't work but PCl5 does? Have you guys ever thought about it? Like, has the question ever popped up in your head, like, how on earth, like, no, okay, but have you guys ever thought about why is it that PCl5 works but not, like, aqueous HCl? Like, if the leaving group ends up being, okay, actually I shouldn't say that, I'll give it ahead. If you're attacking nucleophiles the same, right, in that sense, why is it that PCl5 works? Have you guys ever thought about that? It's a really interesting question to think about. Like, I feel like if you can understand this, right, organic chem mechanisms will be like no problem for you already. Like legit. Just think about this for a second. Like if you haven't thought about this before, think about this. If the attacking nucleophile is the same, why is it that PCl5 can actually like form your hydrogen alkane from alcohol but not HCl-AQ? Aqueous. So like 1 or 2 minutes thinking about it. And then like type out the reason in the chat. Like what you think that happens. Like it can be wrong. Like trust me, this is like actually quite difficult. So like just type out anything that you might think could contribute to this. The nucleophile is the same. That's the funny part, you know. Like the nucleophile that in the final step, right, where the thing is substituted is the same. It's a Cl minus in both cases. Like even for PCl5, you're using a Cl minus to attack the compound. So like, okay, in a nucleophilic substitution reaction, like or any kind of like substitution reaction, what matters? The first thing is like the thing that attacks it, and the second thing is what? Like one of the things that matters is what's attacking the carbon that's being substituted, right? What's the other thing that matters? Think about it. Let me just type it out. We know that one factor is the strength of the nucleophile that attacks it. What's the other factor? Leaving group, correct. Now, since that we know that the nucleophile is the same, right? In this case, it's both Cl minus. What do you think like then what must be changing in order for like one to act better as a reagent than the other one? What has to change? Since we know that nucleophile doesn't change, the leaving group has to change, correct? So let's think about how the leaving group changes because it's like really cool. Like let's see, actually let me use PCl. I'm gonna use like PCl3 instead because like it's fundamentally the same thing, but I have to draw less chlorine atoms, so it saves my time. Let's just use PCl3. So let's have something like this, right? Now something very important that you need to know to be able to like draw this mechanism is that phosphorus and oxygen form really good bonds. So like phosphorus loves like bonding with like oxygen and stuff, right? So that's a hint. Like, does anyone want to guess like what the first step is? If I tell you that phosphorus and oxygen like love to bond with each other, it's like an amazing relationship in the process. Like, what do you think happens in the first step? Let's think about it. And phosphorus can also expand its octet. That's another clue for what happens in the first step. Correct. Correct. Do you guys see what's happening now? A bond forms between the phosphorus and oxygen. So what's happening is I'm just going to draw in one step, but basically what happens is that the oxygen attacks the phosphorus, and then the Cl minus breaks off. So now what you have here, right, is you have this like massive thing over here, like a phosphorus, 2 chlorine atoms, and a positive charge on oxygen. Now does this look familiar to you guys? What does this thing remind you guys of? Like what does the OPH plus thing remind you guys of? It's a parallel to something else that's very good leaving group that's almost like OH. It's like water, correct? No, it's a bit complicated. in that sense, yes, ROH is the nucleophile. And that's actually what's happening for esterification if you think about it. In your esterification, right, your alcohol acts as a nucleophile to kick out your Cl minus for acyl chlorides, for example. But yeah, in this case, you're correct. Like your RH is sort of acting as a nucleophile in the first step. But your OPCl2H, do you guys think it's a good leaving group? Like your phosphorus thingy, do you guys think it's a good leaving group? The answer is yes, because there is a positive charge, it's quite massive and it's relatively well stabilized. So what can happen next, right, is that your Cl minus can just like attack this carbon like freely, like be like, yo, what's up, homies, and then just like kick this entire thing out. And you have this entire thing that you don't have to worry about. Like it doesn't matter, you don't have to worry about it in H2, but then you end up getting your final product. So do you guys understand what's good this part? Because we do, right? It means that your understanding of organic chem is really solid. If you can understand this, right, can do like chemo already, basically. Yeah, it's basically the same thing for PCl5. SOCO2 is slightly different, but yeah. Actually, you guys can, like, if you want, you can always Google the mechanism for SOCO2. It's actually quite fun and interesting to look at. But fundamentally, it goes by the same principle. You have to create either a better nucleophile or a better leaving group. In this case, the explanation for why PCl5 works better is because it makes the OH a better leaving group. Because the PO bond is quite stable, like eventually it forms like a P double bond O oxygen, right, Nicholas? And it forms like your POCl2, right?
PCl5 forms POCl3.
Like for POCl3. Like eventually it forms like a PO.
No, just
like
POCl3.
Yeah, okay.
Yeah.
Actually,
SOCl2 forms SO2.
Yeah, so basically it forms a very stable like final thing after like.
Wait, I'll draw it below. Yeah.
Yeah, once that gets kicked out, right, it forms a relatively stable molecule, so it's a good leaving group. It's a thing. Same thing with H2O. Like when you have a H2 attachment, that's how I was asking that question just now. If you have something like this, right? If you form this, we know that the OH2 plus is a good leaving group, correct? Because if it leaves, it forms water, which is quite stable. It's the same thing for the phosphorus thingy. Like after, like there's a few more steps that happen basically, but eventually the phosphorus thingy forms a relatively stable molecule by itself. Does that make sense, ADV? It's like the same reason as to why like H2 is a good leaving group, but that's all you need to remember. It's just something that's stable once it leaves. It's kind of stabilized by itself. It's just like it's sort of like what water is like. When you have water leaving, right? We know that H2 is a better leaving than OH because H2 is more stable by itself than OH. It's like the thing like this. I think Nicholas is drawing the extra thing. But yeah. Oh, why doesn't Cl minus attack the O plus? Oh. It's because like in that case, right, if I were to scroll back up again. Oh yeah, Nicholas, can you send in a link later for this reaction so you can read up on their own? There's like a lot of good online resources. Anyway, if you look over here, right, if the Cl minus attacks the oxygen, the oxygen is gonna have 4 bonds. So like we know like oxygen can't exactly have 4 bonds because like and it's gonna have like too many bonds basically. It's only a positive charge in that sense because like
No, if you remember your H2, right? Basically, oxygen is what is in period 2, right? So it doesn't have low-lying vacant orbitals, right? For your Cl minus to attack. Yeah. So you cannot attack O plus.
there's just you can't fit in any more electrons. So it's going to kick out the O plus instead. Where do you get that geoclaim?
Basically, the
And
octet is the
yeah,
octet
just think
rule.
about in terms of like bonds as well. Like you can't have like 4 bonds of oxygen, especially if it has a lone pair. Nice, okay. Wait, so ADV, right? Basically, right, this thing forms. So yeah, these are quite stable in water. If you use pH compared to like OH minus.
The reason why
Okay.
SOCl2 is better, right, is because if you use SOCl2, you get SO2, which is a
Which uses a
gas.
gas, yeah.
Yeah. So it
SOCl2
just
is
leaves the
better.
solution.
But pH is more versatile because you can use it for a lot of things.
Okay, nobody knows. Dude.
But do you get it now, ADV? You don't
By
have
the
to
way,
worry
like,
about
there's no need to know the mechanism.
yeah.
Yeah.
This is just for like to help you guys see like appreciate it at a deeper level. Because like in organic chem, right, like you guys are taught a lot of things to explain why they happen. So this is to explain why it happens. So like the benefit of doing this is right is that if Cambridge throws you a random like curveball, like asking you the mechanism for nucleophilic aromatic substitution, you can answer those questions a lot more confidently. But yeah. Let's move on to okay, what do you guys want to cover next? Because these are like the big basics for mechanism drawing. I'll probably spend like 10 minutes going through like mind maps and like summaries, right? But before that, right, do you guys want to go through any other mechanisms? Or anything? Like, is there anything else you want to cover in terms of like mechanisms or understanding mechanisms before I go through that? If not, I'll go through like how to create summaries and mind maps to help you memorize. Anyone? Anything else you guys want me to cover? Like we have quite a bit of time. Like I purposely made this lesson a bit shorter so that you guys have more space to ask questions. Yeah. If there's something in your notes that aren't like in there, right, well, you want to ask, you can just ask. Like, honestly, the discourse of when does it become relevant to me? Oh, that's a fantastic question. Okay, I'll go through that. Yeah, GBD, what's your question first? Isoelectric pointing. Or is it the Deuterion?
It's the pH at which it becomes neutral.
Oh.
Yeah, I can. Okay.
Do you want to take that?
Yeah. You explain the resonance first.
Yeah, I'll do resonance first. So like, okay, for resonance, right, you don't have to worry too much about like too much in mechanisms, but like what you can do to explain how resonance affects organic chem is think about in some cases, right, where like let's say you have a lone pair they want to use to attack something, but what resonance does is affects the lone pair's ability to donate it. So if like let's say like since he's talking about nitrogen, let me just use an example from nitrogen. If you have an aliphatic amine like this, with a lone pair here, versus like aromatic amine like phenyl amine, for example. We know that phenylamine, right? Its electron pair is basically donated into the into the benzene ring. Do you know that, ADV? Are you aware of the fact that like your NH2 like lone pair? Yeah. So what happens is that because of resonance in that case, right, your lone pair isn't as available for like donation. So that explains why like NH2 is a much better base than like NH. Like I mean that your aliphatic amines like this is a better base than your aromatic amines. Better base. In terms of mechanism drawings, right, you don't have to worry about like resonance structures too much. Because like ultimately your mechanism drawings are basically based on electron pairs. As long as you can draw an electron pair, right, your resonance shouldn't affect it. It only affects the properties of your molecules or your reactions and stuff. Does that make sense?
Okay, so right, just to add on a bit, right, there's mainly two cases in which resonance is actually like going to affect your reaction. The first one is when your original reactant has resonance, right? So essentially, resonance stabilizes things. So if your original product has like original reactant, right, has resonance, right, then it's less likely to be it's less reactive lah. So for example, something like benzene. Actually no, a bit hard to explain. Okay, that's the first case where like your original product has resonance, and hence like it would react a bit differently compared to like some other reactants. So for
Like
example,
carboxylic acids, where your partial positive charge becomes worse, that sort of thing.
for example, if you have something like benzene, right, compared to something like propene, and if you were to put like
Br2.
Br2 inside, for example, right, for the thing that is resonance stabilized, aka your benzene, you would get like electrophilic aromatic substitution, right? Basically, a H on the benzene ring will be replaced with an I. But then in the case of like the propene or something, you get electrophilic addition, where you get like what do you call that? Yeah, you add two I's to the thing, right? And you get like 1,2 diiodopropane or something. Yeah. The second case, right, where resonance will affect your reaction is in your intermediate, right? So things that are, if your intermediate is stabilized by resonance, right, then your reaction is more likely to occur. So for example, remember just now in the case of like the SN2 question that I drew earlier on with like the intramolecular whatever nitrogen attacking. And then like, I don't remember who it was, but one of you suggested they will occur by Sn1, right? In that case, Sn1 can occur, right? Because that product, that intermediate, right, was stabilized by resonance, aka because of the benzene ring. Yeah. So
Yeah, that's a very good example of resonance affecting mechanisms. And normally, right, if something like, if they say give you like something like, I know a good example. Let's say they give you something like this, right? Like they give you something like this. Then you say that, normally like based on this, right, you would think that that carbon there would be SN2, would undergo the SN2 mechanism, correct? Because it's primary. Like, if you had no knowledge about resonance and stuff, right, you assume that it goes through, undergoes SN2, right? If I were to tell you that, yeah. So like, but if the question, right, for example, tells you that, oh, this undergoes Sn1 mechanism and asks you to like explain why, right? The simple way you can think about it is, first of all, right, just pretend like you're doing Sn1 mechanism. And let's say the question says, oh, why does this reagent undergo the Sn1 mechanism for nucleophilic substitution, even though it is a primary alkyl halide? Then you try just drawing the mechanism for the Sn1 mechanism. So like, if you draw this, right, this is the first step for the Sn1 mechanism. You get something like this. Now, if you look at this, right, you'll notice that because there's a double bond here, you can have a resonance structure. You can form something like this. And that's exactly why this is more stable than your typical primary carbocation, which is why it undergoes SN1. It can also explain like why you will get something like, the question tells you like, oh, this is the final product, right? This is also how you can explain why you get this. These are just things to like think about. It's like things you can consider. Does it make sense? Normally Cambridge will guide you through these types of questions. So if you're stuck, right, the best way to like think about it is just draw the mechanism first and see what happens. Like if you don't draw a mechanism, it can be a bit tough to see what's going on. But if you draw it out, right, the moment you draw the positive charge, it will be a lot easier to see that resonance can occur. So it's just if Cambridge asks you like, why does this happen instead of this? Like normally they'll do something like that before they test this. Like they won't be like completely unfair most of the time. So does that make sense? You can also unmute and ask if you have any further questions. Okay, that's good. Oh yeah, Nick, don't do the isoelectronic thing.
Isoelectronic point. Wait, have you taught them acid-base equilibria yet?
No, I like
Okay.
skip it basically because last week was a mess. I'll clear the canvas first. You can just draw it anyway.
Okay, so to understand like what do you know about isoelectronic point? You know that it's like the average of 2 pKa's, something like that, right? If you recall. Like JBD, do you remember that? Or like, okay. But The reason why has to do with like acid-base equilibria. Okay, give me an example of an amino acid. Just suggest anything. Something simple actually. Okay, glycine. Okay. We start with glycine. Okay. Oh, I'm damn bad at drawing. Okay.
Wait,
Okay, so glycine, right, has 3 forms in total. Right? There's this.
you
And
have to
then
like
you
draw the proper
put the
one.
net.
I'll draw the proper one for you.
Okay, help me draw.
Yeah.
I'm dead.
It's okay, I'll do it, don't worry. I have the drawing tablet, it's all good. Yeah. Oh, yeah, I need to draw the O minus here, right? Okay.
And because I so perfectly predicted that you're gonna say glycine, I already found the pKa's. It's 2.34 here. 2.34. This is the pKa, okay. And the
Do you just
pKa here.
memorize? Do you have it memorized, Nick, from like iCho or something?
No, I googled it.
Oh, I didn't like looking memorized it for iCho, but it's
Why
okay.
would they make us memorize this? Wait, okay, yeah, okay. Anyway. So right, do you know how a polyprotic acid titration looks like? Like, just say yes or no. Like, I'm quite sure you're familiar with like monoprotic.
He said yes.
Yes, okay. So right, for something like this, right, let's say it starts out from the fully protonated form. The graph will look something like and then you start adding like NaOH, like that, and then there's this, right, and then there's this. It looks something like this. So let's say is it correct? Yeah, it's correct. Okay. At this, okay. So right, do you know what the definition of the isoelectronic point is? It's basically the pH, right, at which the solution is kind of like considered to be neutral. So in this case, it's referring to this, Pi, right? Because this is the Zwitter ionic form, like you see the net is neutral charge, right? And then we start out over here at the start of this graph with this fully protonated form. And this is not neutral, this is positively charged, this is negatively charged. Okay. This is pH. And this is like volume of NaOH added or something. Yeah. So do you know what the pH here is? Let me just put this here.
He said 2.34.
2.34, right? Yeah, so essentially here the pK is pKa1. Because this is the first half equivalence point. Oh my god, I'm damn bad at writing. Okay, yeah. And do you know what is the pH? Here. I'm just gonna write it out because I'm pretty sure you know this. It's pKa2, right? Yeah, 9.6.
This
And so,
man is
right,
smart.
essentially, right, the way that a lot of these graphs work, okay, you can draw that one now. So this is the equivalence point.
Ooh.
And the way that equivalence points work in this kind of acid-base titrations, right, is that the equivalence point kind of refers to the point at which all of the whatever acid-base species in your solution are like this thing. Okay, so for example, this equivalence point here is when all of it is this. And this equivalence point over here is when all of this is this. And this doesn't have an equivalence point because we started from here.
Yeah.
So, this pH over here, right, for polyprotic acid titrations, right, is equal to the average of these two. Yeah. So at this point over here, which is, we call this Pi because this is where all of it is the neutral amino acid, right? The pH is equal to pKa1 plus pKa2, and then you
I'll write
divide
it
2.
out.
Yes.
Wait, why is it basically the unknown point, right? Okay, then I just put a question mark there. The unknown point, whatever on the label, right, is called, it says pKa1 plus pKa2 over 2. It's like the midpoint of those two.
Yeah. And just to avoid confusing you too much, right? Can you guess what is the pH at this one? The second equivalence point. Or how you would calculate it. Yeah.
I don't think they.
They know.
Actually, yeah, they should know. They should be inside the thing.
Funny circle.
Hell.
No, I raised the graph. Calculate based on salt hydrolysis. Yeah, correct.
Yeah,
So basically, right,
epic.
at this second equivalence point, you kind of can assume that all of the amino acid is in this form over here. And then you will
Yeah.
use like your salt hydrolysis thing, like this thing will become this plus
Acid.
OH minus or something to calculate the pH over here. It's the same as like if you were to do a monoprotic acid titration. And then they ask you, oh, what is the pH at the equivalence point? And then like, yeah, you do that, whatever KB equals to whatever times OH minus over whatever thing. Yeah, I think you know what I'm talking about. Yeah. The only reason, right, why this one is different over here, right? In this case, we don't do any funny, oh, does it hydrolyze to this thing or that thing? And the reason why is because it's amphoteric. This thing is both an acid because it can go to this. But it's also a base, right? It's also a base because it can go to here. And in these kind of cases, right, where you have an amphoteric species, right, it is impossible to do any form of calculation based on does it hydrolyze to like this thing or that thing. Yeah. But it turns out it's actually easier to calculate than this because it's just this plus this, like pKa1 plus pKa2 divided by 2, right? And just to extend it a bit more, right, if I were to do the same thing for something like an actual like polyprotic acid, right, like H3PO4 to H2PO4 minus, right, to HPO42 minus, and then to PO43 minus, right? This would look like this right? You see three equivalence points here. And then these two species are amphoteric because they're both acids and bases. And if I'm right, the pK here is like 2.13 or something. This is 7.24, I think. And this is 12.3, I think. Something like that. Yeah. And so it's actually super easy to calculate these two pHs. These two. Yeah. This one over here will be 2.13 plus 7.24 divided by 2. And then this one over here will be 7.24 plus 12.3 divided by 2. Make sense? Yeah.
Okay, fantastic. You guys get
So
that?
this is more acid based than OutChem. Yeah. For H2CO3, yes, it works for every single acid that is polyprotic as long as it's an amphoteric species. Yeah.
Mm.
And so right, just to extend a bit more, let's say you had like some amino acid that's not glycine. Okay, let's say something like shit, I forgot the aspartic acid.
Oh.
Yes. It looks like this, okay?
Yeah, I'll scroll. Let me draw it. Yeah.
This is no zito ion. Shit, wait, how to draw this?
Bro.
Like that. I'm very inconsistent, clearly. Okay. But then in this case, right, you can see that there's more than 3 forms. Because for glycine, right, for glycine, there was like 3 forms. The one where it's all protonated. Then there's the isoelectronic one. And then there's the all deprotonated one. But for this one, right, this one there's 3 different types. Okay, actually, let me just draw out all of them. So you can start with this. Then there's like I I don't know what pK is. pK is okay. Actually, I don't care about the pK.
Just draw the
Right.
free forms.
Yeah, I'll just draw the free forms. I'm just gonna assume that.
The top ones. I mean, for amino acids, both the acid and base are usually weaker than. But okay, listen. Basically, there's multiple forms. So that's the point here.
Yeah, the
Then
point is that this
there's,
has multiple forms. And so, what you need to know for this one, right, is that which are the two pKa's you take? That's my question. I know I'm drawing this a bit wide, but
Yeah, for the first thing you guys need to do, right, is to identify the isoelectronic species. Like among these four, right, which is the isoelectronic species?
oops. It's H2.
If you like the second one, correct, right? So that means in order to get like the right one, right? If let's say this is like let's say pKa1, pKa2, and this is pKa3, right? What would be the this is like assumption. We don't know what the actual one is because we don't know the like. What would be like the pH of this? Like if you knew pK1 and pK2 and pKa3, how would you calculate it for the pH of isoelectronic point?
Yeah, I'm pretty sure you know it already. It's these two, right? And then, if you were to go even further, let's say you have some funny like something like this. I don't even know whether this exists. Right, something like this. To hold on, which one's more acidic?
It's just more basic. I'll presume the one that's farther away from the amino acid branch. I would say the top one's actually more basic, honestly. I mean, like the top one's more likely to.
Yeah.
I think. But the PK is usually quite close, so it's hard to say. Unfortunately. But I think it's actually within the syllabus to determine which one's better, but whatever.
I think at this point, you kind of figured it out already, but I just want to like draw it a bit more so that I can make sure that you actually know everything. Yeah. Wait, no, this is wrong. We're trying the same thing. Wait, no, wrong one. Okay. Yeah, this one.
Okay, I'll draw it for you.
Yeah, let me draw the last one. Yeah. In this case, which are the pKa's you take? Is it pK1, pK2, or pKa2, pKa3? Wait. 2 and 3, right? Yeah, because this is the isoelectronic one. Okay, yeah, that's it. I think you get it already. That's PIA, very detailed. Do you get it? If you don't, can just ask which part you don't get and I'll try to explain.
We do it directly.
Okay, nice, fantastic.
Fantastic. Any other questions for Cam? Or any?
I know that quite a while, but yeah, just continue asking.
But I think that's a fantastic concept. Like it tests like so many parts of acid base and organic chem that I think it's very good they answered. Good, thanks a lot, Nicholas. Can you like type of progress in the chat for Nick? Like he has kindly volunteered to help for this without having to. Progress, yes, okay. But any other questions for Ocam? If not, we will move on to mind maps and summaries. Like feel free to ask anything like legit. Like we are here to help you. And if you have any questions separately, right, you can just like drop them in the H2 chemistry chat after this. Like either me, Nick, or like someone will come and help you out. That's the benefit of Discord. Not gonna lie. So like make good use of it, basically what I'm saying. It's basically what I'm saying. And if you have friends, right, that think could benefit from this, ask them to join as well. But anyway, if not, I'll move on to how to make your mind maps and summaries. So like unfortunately there's a lot of things to memorize for Ocam because that's the world we live in. But in order to make your life easier, right, there should be two things you'll be doing. One is mind maps. Like think about possible reaction route from let's say like starting a certain molecule to a different molecule. This is good, right? Because in a lot of questions like where they ask you to let's say try HCl gas, this bunch of things. Because let's say for elucidation questions or like the reaction mechanism questions, right? If you draw mind maps, you'll be more accustomed to like how certain things will react to form this. So for example, if I want to convert this to like this, right, I will know that it's another case. It just speeds up your memory links. Alright? So for mind maps, the key is draw by functional group. So draw a separate mind map for first degree alcohols. You can draw a separate one for like second degree and all that if it's important. Or you can draw like a separate one for primary halogen alkanes. So basically, right, and all that. So just draw mind maps based on functional group, but do summaries based on type of reactions. That's the important tip. So for mind maps, I'll draw by functional groups, right? But for summaries, right, what I would do personally is do by like type of reaction. So I'll do by Sn1. Okay, let's do SN1. Let's just do like oxidation, for example. Yeah, it's right here. So did I put that? Oh my god, I put AQ. Oh my gosh, I put AQ. Dry heater gas. But anyway, right, okay, this is like that. If, what I'll do for summaries, right, is I'll do it by type of reaction. So I do oxidation. And basically what you have to do is that you have one column for like what you're converting it to. So for example, right, let's say I want to convert the primary degree ROH to a carboxylic acid, let's just say. Like, yeah, let's just do a carboxylic acid. I'll have one column for the reaction that's occurring, so this is the reaction column. Then my second column will be reagents and conditions. So this is how you can make your summaries. If you guys don't have time, I'll probably be making the notes for these and putting them on the website later, but yeah. So reagents and conditions. So this is basically the main tip. And this is what I recommend you guys to do for memorizing Ochem stuff. So for reactions, like for mind maps, do by functional group, and for summaries, do by reaction. Do you guys get that? If you guys get that right, that's pretty much it for today's lesson. If you have any more questions, you can just ask them now. Or if not, that's pretty much it. You guys can go, but I'll send you guys a feedback form first. You can just fill it up because feedback is important. If any questions, you can feel free to ask them now. So yeah, just feel free to like fill out the feedback form, and that's it for today's lesson. I hope you guys enjoyed it and learned a lot. So yeah, if you have any questions, you can just unmute and ask. Even just like talk to me and Nick for like random stuff. You can do that too. Like we're pretty chill. If not, you guys can go now. Bye bye. Have a great weekend, guys. Go ahead. Stop recording.